lecture from last week?
It should be up online. So all the lectures should be up online. So if you go to media gallery, as soon as I get done, I pop these out and upload them. Whatever it takes to upload time.
That's on Canvas, right?
Should be on Canvas, and then you should go to media gallery.
Yeah, I have no clue. There's a little okay to access your account thing you do, and then they all show up.
Yeah. So evidently you have to give permission. So that doesn't show up to me at all.
Yeah, because you gave them.
Because I gave it to them. It doesn't even show up in media gallery for me. It's my media.
It's yours.
So it's, yeah, it's, but anyway.
We can go back to
Okay,
this report.
so we're gonna start off. Today we gotta talk about basically dependence and data hazards and things of that sort. If you came in a little bit late, the review and question sheets are around there. Just as my note to it, please do give feedback on those. It's about the only way I can really tell for certain where everybody's at. So it gives me good information on how to aim stuff. All right, so the first part should be a little bit of review, and then we're gonna extend this into where things hit with like Tomasulus and some of the other techniques that go on. So first part of this, let's start breaking down some of the areas. What are the three types of hazards? Because in order to do instruction level parallelism, we gotta worry, whenever you speed something up, you run into more dangers. So there's three classical groups of hazards that we break down. Potential dangers for, that we need to overcome in order to exploit instruction level parallelism.
Is that RAW or is that?
That's a sub of one of them.
All right,
So,
data
the first one, that's data. Right, and this is when we get the RAW and so on. Okay, and we've got two more.
Structural.
Okay, structural hazards.
Control.
And control hazards. Let's go bottom up on these, because we spend most of the time up here, but we do have to think about some of the rest of these. Control hazards, what are those?
branches.
Branches. Anytime, you're basically not following sequential instruction loading, you're gonna run into a potential hazard that goes on. So this is if statements, technically case statements, anything else. Are all of them equally difficult?
I'm gonna say no.
Yeah, they're not all equally difficult. Because there's conditional ones and there's unconditional branches. So if it's an unconditional branch, like a subroutine call, there's no question. So the only thing you have to do is figure out where that address is to load the next instruction. There's no question whether that's any good or not. And in that case, I know where I'm supposed to go, so if I have done some type of a scheme that preloads or things of that sort, I can fully take care of unconditional ones that's going in. This is also what makes things like case statements better than a bunch of nested if-then-elses. Case statements are unconditional, whereas nested if-then-elses are conditional. So what you want to do with each one of these is think, what type of an instruction is it going to break down to? So that becomes one of our important underlying areas. All right, how about structural? What are those?
Your functional units, is that like, you don't want to tie up everything in the same hardware or something?
Yeah, or I just don't have enough hardware to do
To
it.
do it right, yeah.
Think about this one, for instance. This is easiest to understand under multiple cycle execution. So multiply is going to take a long time. If I were to make multiply finish in one cycle, as in make a cycle long enough for multiply to finish, everything else would be taking like 1/100th or probably closer to a 1/10 of a cycle, but a ridiculously smaller amount of time. So I'd be wasting a lot of time on most instructions. So it doesn't make sense to do it. So what it does make sense to do is kind of pick your cycle time to make sense for the majority of your instructions, and then multiply is going to take multiple cycles. Well, if I've only got one ALU and it's in the midst of multiply, no other instruction can come in. So there's a hazard here when I'm trying to make things parallel, that there just isn't enough resources to solve that problem. Similar types of things happen if I'm doing a memory load and I actually have to go all the way up to ramp, which could literally cost me, 100 cycles or so. Depending on my system, could cost me even a little more. So those ones could easily get into situations where I don't have the resources, I don't have a unit to put on it. So this one happens all the time, for instance, in network computing too, your buffers overflow. Right? So you're having to queue things up. You need enough resources. So think whenever you see structural, think this is talking about the hardware. The parts that can't change, it's just a fixed amount to go onto them. So structural hazards, you just have to assess. Sometimes you don't want to solve the structural hazard. I mean, imagine it's a rare situation and it would be really costly to add the extra structure and solve that problem. And it can be solved by just making somebody wait a little bit. It's probably more cost effective to make them wait. If it really becomes problematic enough that people are going to pay extra money for it, now all of a sudden you allocate the extra resources and build them. But sometimes it's so rare that it's just, to get the extra resources there, you have to take from somewhere else. So, structural hazards become, this is the core of the hardware design area. What do you pick to do? And you have to weigh off all these other trade-offs that go on. So this is just a selection process that goes in. Now, for a normal pipeline, if I run into that multi-cycle problem, right? So let's even just consider the MIPS, because that's what the book works on. Fetch, decode, execute, memory, and write back. I'm going from one to the next as it's progressing down. Let's say I do have an instruction like multiply that can take on these. How would I pipeline that? Right, because remember, for each one we have to put in the buffer registers to separate them out. And it's pretty much a straight line as I'm going through, right? So if something's in execute doing a multiply that's in here, and I've got some instruction in X1, some other one X2 that's going through, how do I let them come over?
Out of order execution.
So I agree, that's what you're trying to do. They're now executing out of order. So that's what the goal is. The question is, how do I build it? Because as we built it, we just literally, if you remember, we had the register file and the control unit, and the control unit has wires, and the register file sends out 2 bits, and you got the sign extender, and it sends it out, and that goes in here. And then we had a series of just, we take the second input and we go into a MUX, and the A line, and it goes into the ALU. Right? Ignoring the branching and whatever else is going on. I mean, this was the basic data line, and that could either be an address which goes into memory or it comes around, and then in write back, you got another MUX that carries back around to go in. I mean, that's basically your data pipeline. How can I let something execute out of order?
Well, you kind of take what we've been doing with the last lab. You have those reservation stations that maybe you have multiple ALUs that you can work with. Maybe multiple operations.
So you can start seeing where I can start blending these areas together. Tomosulu's approach was reservation stations. I can even do one step before that with reservation stations. I can just do a busy flag on these to say whether they're going to read or not. And I can just have something that's going to put just a register right on the edge, right? That's going to hold their inputs for it. Right? And I can have a flag that tells me whether it's busy or not. If it's busy, I won't let its clock pulse. I'll just hold the clock low, and you can't load anything to it. And then externally we can find out, and I can call this, some little unit here. And then I can reproduce that unit. And then I can just send it out and say, whoever is the highest priority one that has this grabs it, and the highest priority one grabs it. And it locks onto it, and it starts working. I can build as many of these as I want. I can just run the wires, right? Just like we did on our issue, it can go everywhere. Now, once you notice this, right, these are just buffers holding it going. I can then say, hey, look, that is potentially slowing down my unit that's doing issue. Right? Because decode does two basic functions, one of which is technically decode 1 and the other is decode 2. Decode 1 is where you're figuring things out, and decode 2 is when you're sending it to the correct unit. We call that sometimes issue, and we'll sometimes split those apart into two areas. That slows down the issue portion. Well, if I just had a reservation station, I don't have to worry about trying to find that. I shove it out there, and the reservation station has to make sure it gets it to the right area. Right? I offload the task that's going in. So that allows me to then get multiple ones that can go. So I can now add them in, but that adds new challenges because what happens on the back end? Right? I mean, you launch them in order, but on the back end, they're completing out of order.
You have to reintegrate things.
Yeah. Right, so I've got to figure out how to handle that backside to make sure that finishing out, or because it hasn't updated registers yet. What if something requires data from one of those registers, right? So there's a lot of options out there that could potentially happen. So I create more flexibility, I avoid a problem, but it opens up a new nest of problems. They're not unsolvable, but they are something you have to be aware of so that you can start making solutions. Does it make sense? Okay. So that's kind of a typical structural problem that goes in. We notice the difficulty and then we start taking a look at how do we have to handle them. Now, we started on this one. We've got data hazards and raw. Right? What's a raw hazard? Or read after write?
Read after write. Let's see.
Right? It's got another nickname, a something dependence.
Isn't that when you said data, or?
Call them true dependencies.
Okay, true.
Okay? I mean, sometimes I do the anti-dependence, all the rest. I'm not worrying as much about some of those ones, but this one is an important one to remember as a name. And it's an important one to remember because it tells you something very fundamental about it. This is the only one that really is out there. Okay, the other ones are just dependencies in name. And what I mean by really out there is this. When you look at the arbitrary algorithm that you're implementing, this one is saying the next one needs the value in order to go on. If I had infinite resources, all the other ones would go away. Okay? But this one is one that doesn't go away no matter how many resources you have. So everything else ends up being a resource or a sequencing type situation. This one is true. It says it has to go in this way. Because if I'm asking you to add 2 plus x, and I'm like, what's the answer? Can't you give me the answer? I mean, it's just a dependence. You're depending on x. Can we violate that? No, you have to know what x is, right? But if I'm saying somebody else is going to also be using your x value, does that stop you? What if I tell you somebody's going to use your result? Does that inhibit you? It's not a real dependence in that sense, right? If I'm telling you, you're both writing to the same area on the board, you don't really, I mean, that doesn't affect what you can generate. It'll affect other people down the line whether it happens, but if I gave you each spots to write your answer, that problem would go away. So this is the only one that really you can't make go away with anything. All you can do is you can try to get the answer there quicker, and all the techniques to handle this revolve around that. The two most basic solution techniques, anybody remember?
I remember like forward data. Like
Right.
you would
So forwarding, this is the fast one. Right? That's the really cool one. What we're saying is, hey look, your answer is available if it's a calculation right after execute. So why not pass it back? Or pass it back whenever you need it, just run extra lines, and I can just expand these muxes, right? And I can just pull my solutions back from wherever I want. Right? So that's kind of a neat solution technique that's out there. I can just pull my answer back. that's forwarding. So that lets you grab it, and that's very useful inside a pipeline. So that'll speed it up if the solution's already there. Will that help for memory accesses? Only one cycle's worth, right? For that last little bit before, I can bypass. So I can save you potentially one cycle if that happens to be where it's positioned. Yeah, maybe that counts for you. If you're doing a whole bunch of them, it could help. I can't make the memory one go away, but I can lessen it a little bit by doing those type of operations. You know, is there anything else that would help lessen memory operation ones? This is kind of a tricky one because I would actually have to change the way I built my hardware. But what if I took memory and I stuck it back at the execute stage? You get one cycle earlier, wouldn't you?
Maybe, yeah, right. If you do-
Okay,
if you do-
so now you got a trade-off. Now, what would be the disadvantage? What was I using, why did I put memory after execute? I was using the ALU to calculate the address. So it was your addressing mode.
Because you need more.
Because we had a base, you know, the constant plus
Yeah.
an offset, right? You know, whatever this is, like 4 or something,
Yeah.
right?
You need
So
that.
it was a base plus offset. So since I had to do a plus, I had to do addition, I used the ALU to do that addition. Now, if I were to move it back one, you could only have a register mode, register only. Can I do everything with register only? Yeah, absolutely. You just have to pre-calculate stuff. It adds one extra instruction. Oh, so is there no advantage?
If, you know,
I might be able to put that instruction in parallel so it doesn't take any extra time. Remember, your thing is latency, right? For these things, what matters is how long does it take through that pipe. So if I can put things in parallel, I hide your latency because you were already spending that time. Right? You know, if you're like really great at cooking a steak and I'm like, oh, I just don't want to eat just steak for dinner, I'd like to have a baked potato and some whatever else, you know, and you're like, I don't have time to cook that. If I went in there and cooked at the same time as you, we could get things done in the same amount of time and we get more stuff done. Same idea here, right? If we can parallelize it, we can take advantage of it. So separating that out can actually speed it up. This is one of the risk principles. The simpler I make your addressing modes, the simpler I make your instructions, the easier it is to chunk them out and then put them in parallel. Because now I can start running things earlier. And the earlier I push them and the less work I make each instruction do, the shorter I can break that down.
So that would be like a 4-stage pipeline, so how small can you really get?
Well, you could just do it in one. Now, the reason why we break it up is because I want to put things in parallel. Now, people noted that your speed up of a pipeline, if I have n stages, I can get up to a speed up of n. So there seems to be no advantage to reducing it. However, if what you have done is arbitrarily dragged your stuff out, there's actually no advantage to it, right? The advantage is if multiple things are happening simultaneously. So making a bigger pipeline, but that really isn't actually exploiting any parallelism. Turns out that all it does is increases your latency that's going on, and so the instructions do not run any quicker that's going in. So, you know, you don't want to make a fake deep pipeline. And they discovered this. People started chunking them up. There was up to, I think, 32 stages was the largest I ever saw that was in there. Everybody's pretty much under 10 now that's going in. Because there are legitimate things, like I mentioned, decode is very often split into 2 stages. One to decode and then one to issue. That goes on. And things. So it turns out if you've got a legitimate thing you can parallelize, it absolutely makes sense to parallelize it and speed it up in the pipeline. If you don't, then you're just wasting time. You just make it look better, but it doesn't actually net a performance advantage. So while theoretically you could get up to a 5 times speed up, if nothing's happening in that stage, like for arithmetic commands, what goes on for arithmetic or logic commands here? Nothing. So all you're doing is delaying when the answer arrives. Right? So, you know, while it looks like, ooh, I got a 5 times speed up for an arithmetic command, there's really only 4 commands and 1 command of just sit there and do nothing. Right? So that's why I'm saying about it's a fake depth of the pipeline that's going on. And arithmetic and logic commands make up like about half of your commands out there. So it's a really sizable chunk of what's going on. So there's no real advantage. So 4-stage pipelines in that sense for this type of a structure I think is more sense. But you would have to simplify. Memory is the beast in this thing. Right? The problem with it is that, you know, memory has that addressing mode. So you'd have to change your addressing mode. You know? There's a bunch of other ones we can talk about. Branch also. Branch, you know, in this sequence doesn't happen until here, but it really could finish here. And the only reason it takes an extra cycle is because they allowed the command branch equal and not just branch equal to 0. Right? If you just did branch equal to 0, it's a very simple thing to check if something is 0. If you're trying to check if 2 things are equal to each other, you have to subtract them and then see if the result is equal to 0. The subtraction requires this. So you don't get the result of the condition till later. Right? This, and then it's really fast to generate the 0 that goes on. It's just a reducing OR. Right? If they're all 0, then you'll get 0. If any's non-zero, you'll get a 1. So you very easily get an answer out of that. So this one is, you know, easily reduced also for branching by a stage. But the bigger you make your instruction set architecture, the more options you give people, right? The more complexity of your pipeline, and you start making wasteful extra stages. We want to, really, you want to find the smallest pipeline that you can do, and then break it up into efficient parallel pieces. That will get you the best overall performance. All right, we feel good with these as going and about how raw works. What's the other option for raw?
Slipping.
Slipping. Yeah, you often hear people talk slips or stalls. Technically speaking, it's most of what you're doing. Like if I'm doing like, let's say this is a multiply here that's going on, you know, and I've got the fetch and the decode. I really want to do a slip. What's the difference between a slip and a stall? Stall stops everything. A slip is one thing's held and the rest moves. Okay? So we really want to stop fetching and issuing stuff, but we want what's there to keep going. If I had a multiply and I stalled the system, right? Technically everything's waiting that's going on, which means these ones can't continue. Now, technically the combinational logic will continue in between the stages, but what if there was other instructions going on? They can't finish either. Right? So you kind of want to allow these ones to keep loading based on whether there's something ready for them. And we call that where it can conditionally keep moving to finish things out. We call that one a slip. And it usually is a couple cycles faster than actually stalling. Technically a stall is what you have to do if you've got a memory slowdown. Because you have to wait till the memory's got its answer. You know, I could do that also for these others, so I'll put them together. But in general, if you can slip, it's better to slip. You know, if you can forward, it's better still. All right, what are the other two? These are both name dependencies, which means that it's based on where you're storing them. So you've got a certain number of registers. I stick a value in register 13. I stick something else in register 13, but it's a different value. So I'm reusing it. Since I'm reusing it, there's a chance they could collide and I could get them in the wrong order. That's really the entire problem of what's going on here. Now, that's the basic underlying thing. But there is a difference between these, and there's a difference when they happen. right? What is a WAR hazard?
Right after a read.
Okay, it's a write after a read. How can that become dangerous? Or give me a code sequence that will generate that problem.
If it's out of order, you change the value before it's read.
Okay. So a write after read happens, like, let's say for instance, I've got, an add to R3, R2, R1, and let's say I've got add R2, R4, R5. I've got a write after I read it. Now, if you notice, this is not a problem as long as they are going in their order. If everything is going in their order, I do one instruction, I move to the next, there is no problem here. If I pipeline it, can this become a problem? I mean, read after write became a problem in a pipeline. Can this be a problem in a pipeline? No, it cannot. Why?
Still in order.
It's still, yeah.
Yeah, because this will read long before this one ever even starts, so there's no chance for it to read the wrong value. Right? The problem, this one is starting at the very beginning, right? And this one's thing happens at its end. So could out of order completion cause this problem?
Maybe.
What if I launch them both at the same exact time? They just finish it different. Is there any way for this one's answer to go into that one's beginning?
No.
Because this one and this one will read their values, then they'll calculate. So if they start at the same time, this one's already read its value. It still can't happen. So for out of order completion, not a danger. So when can this one be a problem?
Maybe if you're waiting on loading the information from R2 and R1 for some reason, because maybe you have a read after write ahead of it issue, and the computer thinks, oh, well, I'll just fetch the next instruction first.
So yeah, imagine I was being held for R1. It was loading from a memory operation. So therefore, this one, 4 and 5 are already there, so it wants to run it. So that's an out of order start. The only way you can run into a problem on this type of instruction is an out of order start. Now that's how I could do it. I could have had up here, load word to R1, 0, R6. And that could be hanging around for a while, right? Which means this one's hanging around for a while and says, oh, 4 and 5 are good, away we go. It finishes, because it's an add, long before that one does, it changes R2's value, and away we go. But the problem has to happen with an out of order start. That's the big thing to remember with these. I don't usually see it emphasized in books. People give you all the things, it's events, whatever, But ignore those. That's not what matters. Who cares about the name unless the name tells you something important about what's going on? What matters for this one is it's only a danger if they start out of order. Can Tomasulus do this?
Do you mean solve the problem or?
No, can Tomasulus run into this problem? Is war a problem for Tomasulus? No,
So you're already loaded this up.
because they issue in order. And the first step of the issue is to grab the value of the registers. And when it grabs the values of the registers, if it doesn't have the value, it grabs who's producing it. So it no longer is looking at that register. It knows who's producing its solution. For Tomasulus coming into this thing, this would get stuck into, like, say, reservation station 1. And this one's getting stuck to reservation station 2. And R1's not done yet, so this one it would get its value. And this one it would get it's being produced by 1. So when this one comes and updates R2, it's being updated from reservation station 3, and this one during the update stage goes reservation station or, you know, RS3, I don't want that. I want RS1. So it'll wait around forever for RS1 to finish. As soon as RS1 does, it knows who it's going. It goes, oh, that's 1? Okay, that's my value. It has no problem because it issues in order. So therefore, it can then track. The reservation stations sometimes become what we call register renaming. Because instead of going to R1, you're now looking at reservation station 1. So I've renamed R1 to reservation station 1. And now it doesn't matter what you change anywhere else, how you reuse register 1, it's not going to affect the fact because everybody who needed reservation station 1's value is waiting for reservation station 1. So this, what we call renaming thing, allows me to get some extra scrap variables at the time. And so that's the real big advantage that those reservation stations buy you by giving them a name and allowing it to have the update. So that's what those updates, when you're creating those, if you don't have the value, then you're storing who's producing it. That's what the producing buys for you. The producing buys for you the fact that it can correctly track what value does it want. And it doesn't have to keep going back to the registers and the registers to resolve this, you know, who knows how deep the problem goes area. Does that make sense? So the only danger would happen is if I run out of scrap variables to allow me to do the renaming, right? So how do we handle that one, Thomas?
Have lots of them,
We have lots of them, but eventually, I don't care how many you have, right? I can always,
tangle them up somehow.
right?
Have a flag that goes some falls, no more.
So look at the error condition that's inside your unit, right? When you run out of those areas, what does it signal?
Error.
Yeah, an error and that I'm full. And so now, whoever is doing the issue gets that thing and says, that instruction did not get issued. So it goes, uh-oh, everything's full. I can't do anything. So it's got to wait. Right? So now you go back to stall slip. This is our universal, it always works. Right? You can always go back to stall slip. We don't want to go back to stall slip. Why?
Slow.
It's slow, that's it. Right? So, but I'd rather be slow than wrong. So therein lies your trade-off that goes into it. So, you know, if I've got no choice, I'm going to go back to it. But prior to that, I'm going to do whatever I can to keep my speed up. Okay, right after right. I'm writing. Problem?
Only somebody reads it.
So what you have to do, this one, everybody goes, that's not really a problem. The real problem that's going to happen is there's going to be a read later and it's going to get the wrong value. Yes, but that doesn't emphasize where the difficulty is. If you think about these values that go on, if they happen in this order, let me call this one 2, just call them by their numbers that I put up here. If I'm looking at register 3's area, right, it should have the value that comes from 2 for a period of time, and then it should have the value from 3 from then on. Okay? And how many reads happen after that?
Doesn't matter.
Right? Could be a whole bunch, who knows? Right? So there's potentially a whole bunch of them. It's not just one of them that's the problem. It's a whole bunch of them that you have no idea how many of them there are. Right? So theoretically an uncountable number of them for all you know. If I flip their order, what do I end up with? It means all those unknown ones are getting the wrong value from then on. Right? What if 3 is really fast and 4 is slower? R2 is lower there, that goes in. All right? So when could this become a problem? And to find out when something becomes a problem, you gotta ask, when will it manifest within the instructions timeline? Beginning or end? The problem is always on the right, which is
Yeah.
the end. The reason why I didn't have as much of a problem with the war is because one of them was at the beginning. But in this case, they're both at the end. So in order for them to be out of sequence, who continues on and the wrong one continues on, all I need is for the ends to be out of order, right? Because what if they start at the same time?
They don't finish it at the same time.
These ones won't finish at the same time. I didn't require any fancy weight on here. R1 could be a legitimate value. This'll, if you give me extra structure in a pipeline, these will still finish out of order. And you have no idea how many things are going to get hit. Could this happen in a pipeline? A regular pipeline, our first version? No, because you can't do out of order. Can this happen in a pipeline with multiple units that I can issue to? Yes. So remember I said you add that structure, and now things can finish out of order, you've sped things up a bit, but you've introduced a new problem, and a new problem that most people find, huh? Because who cares, you're both writing, right? It doesn't affect you, it affects unknown ones later. The problem with that one is you won't be able to figure out how to make them work out right unless you fix it at the time. Yeah.
So the only time that, like, because it's kind of very pointless, line 2 is kind of pointless. And so I guess the only time it would be important is if you had 3 instructions you loaded and maybe it was
Yeah.
used in the...
There could be something in between,
Okay.
okay? And that's implicit within what's going in this. That somebody else is in there and who knows who else is going on. But that's not the danger. Because, if I were to preserve those ones and I were to, just take this one and flip it up, right? I could even notice that there's 1 or 2 after that go with this and I can grab that block and move them up. Assuming that they're independent. But no matter how far out you reach, what's used after that? I mean, how far do you have to go to find out how far that thing's used? That becomes like a nightmarish task that goes on. Right? So that's why this one is difficult. So I agree with you, yeah, it would be completely pointless unless there's something in between. But there's always something in between using it, or you're right, just cancel the instruction, who cares? With the exception, unless, there are some times when you do like a subtract and you don't use the value, but it sets a condition code in the system. And so there's a hidden condition code that's used for branching. So sometimes you don't use the value. There's sometimes a special purpose register that's independent of this. That it sets up, was it negative? Was it 0? Was it positive? Did you get a carry? And it sets those condition codes, and then you can branch on overflow, branch on carry, branch on negative. So there are some systems, depending on how they do their branches, that use condition codes, which are hidden from your first look. But, assuming that you're not worried about that going on, there would have to be something else in between there. But the problem just comes in this, you can track some of it, but it's really hard to guarantee nobody's ever going to use it. Because this one stays on indefinitely. Right? Unless you find another instruction that's going to replace it with some value 4, right? Now you know it's done. But how far could that be and where does that go, right? When you're having to build it in hardware, that would be difficult to try to track all the repercussions. So what can I do with it?
You'd like set a condition that if you have multiple things in your reservation stations or whatever that you want to write to, you just ensure that the first one you put in is executed first.
But remember, it doesn't matter whether it's executed first. It matters when they finish, because I could technically let this one start first, and that one start second, and this one could take 20 cycles, and this could take 1. Right? So even if it got a head start of 1, I could still do it. I mean, if I went in a race against Usain Bolt, if you gave me a lead and there's only one track and he's not allowed to pass me, I can beat him. Okay? Just reality. But if you give 2 lanes, you can give me an awful big head start. He's gonna take me down hard, you know, unless I pay him enough, maybe. Yeah.
Well, when you fetch and decode the instruction, you already know its destination, right? So can't you have just a table of destination registers, and then if something else reads in and it conflicts against something that's already in the table, then you have to wait for whatever instruction is associated with that to finish before you can write back to that register.
Okay, so that's a technique we call scoreboarding, which we take a scoreboard into our system, and you basically track them, and then we reorder them. So we call that a reorder buffer. So we let them all update back into our main list, and then we write their answers out in sequence. Okay? Now, that's helpful in other areas also. It helps me with the control problem that goes on too. Right? Because if a control thing's going in, I can now run extra commands. I could stick the result into this scoreboard, the reorder buffer that's going on, and then, you know, I could wait if the control ends up going the direction that I thought it was. I just let those write really quickly, and if it ends up not, then I just delete them out of the queue, and no harm, no foul. And so that type of a thing with a reordering is useful, not just here, it's also useful to take care of control hazards. So worth mentioning, right? Is that what we do in Tomosulus? No, and it's got to take care of this, right? Because I got multiple units. They finish in whatever order they want, but there's still not a problem. So how does it handle it? So it all is revolving around the register, right? Does it get the right value? So the trick that goes on in Tomosulu is this same renaming scheme. Inside your registers, right? Yeah, whatever, you know, register 00, so I'm not going to write it. Register 2, register 3, and we've got values, and then we've got who's producing you. All right, so originally, let's say it's got 17. And if it's being produced by 0, notice we always start our reservation station numbers with 1. The reason is reservation station 0 doesn't exist, so it's the condition, meaning the value is good. So inside the registers, if they see a 0, they go, oh, 17, completely good. My value is authoritative. Now, for register 3, when this one gets issued, it's being produced by this command, which means it's being produced by station 2. Any other instruction that comes after it is going to get the, you're being produced by 2, so they get the correct one. 3 comes in, right, this add, and says, I'm producing R3 now. My reservation station is 3. Okay, it doesn't matter, the 2 is finished. I don't need 2 anymore, so just dump it. Right? Anybody who came in between was issued in order, so the write after read problem is not a danger to us because we issued in order. So this problem for the intermediate ones is right here. It's not there because I issued in order. The completion one doesn't matter because the reservation station number is recorded by the register. And the register is no longer going to listen to 2, it's only going to listen to 3, which means it'll grab the correct value. So whoever comes later is of course going to get the correct value because the register has the correct value. And it knows which one to listen to because it picked the renamed value. So that register renaming takes care of this problem. All right? So I could do it by scoreboarding and reordering, but then I have to make everything finish in sequence. I can do it with the renaming, and it still takes care of that problem. Does that make sense? Since it only matters the order of completion, if I make the registers and the reservation stations update by the reservation station number, all renaming works, and the problems disappear on the data hazards. So is Tomosulu's, because it's obviously faster to do that than to put it into a reorder buffer. Is Tomosulu's always better than a reorder buffer? I saw a no, and that is correct, it's not always better. When does it go bad? What's its problem? Because its problem isn't any of these. Is it innately a structural problem? No, because you can have as much structure as you want, right? It's got no more innate structural problem than anybody else has a structural problem. So what's the problem?
Branches.
You know, go Sherlock Holmes, right? Once you've removed all other possibilities, what remains must be the answer. So it's a control problem. And here's the area that goes in. What do you do when it's a branch? When you hit that branch, it doesn't know if it should allow it to complete. Tomosulu's lets them complete very quickly and without interference from a central authority. So once you've launched them, they're gonna go. So now what do I do? If it's a control thing and I discover, oops, I shouldn't have launched that, what do I have to do? It's like launching a missile and you discover, oops, shouldn't have launched at that target, right? You know, I mean, I'm either sending a condolence letter or what?
Push the big red button.
Yeah, I gotta push the self-destruct button, right? So I've gotta have a way to track it and self-destruct it to prevent it from writing. And you better hope it's not a really fast missile and a close target, right? i.e. a short command. Because if it was a short command, it could have completed before you discovered, right? Like and. And is a very short command, right? It's one gate. You will not have solved your branch, but if you launch an and command right after it, that and will finish before you know whether branch is right. Add, you got a chance. Add is much slower than and is. It's at least takes 6 times as long and up to the number of bits times 2 as long, depending on how the person writes their thing. So, you know, on a 32-bit machine, that could be 64 times slower than and. You know, it could be less, depends on the type of structure you do, but that's a worst case. You know, that would be a replicatory versus and. But if I put a short command in there, you're in deep trouble. So the only thing I can be absolutely sure of once I hit a control thing for Tomosulu's is?
Stall.
It always works, doesn't it? Right? Completely safe, I just stop you. Your performance tanks, but you're safe. Right? Now I can look at the type of instruction and say that one I can launch and I'll have time to self-destruct it. But you're still stuck with that problem of you've got to be able to self-destruct. Does it make sense? So anything I can do to Tomosulu's that will let me handle the problem of control?
Scoreboard?
I've already got a little bit of a scoreboard. I could put the reorder buffer back in. Now that slows when they complete. All right? But it would allow me to handle that problem and I could move on. So when does a reorder buffer have an advantage? It's got the advantage after a control. I could do a hybrid system where I let it complete whenever it wants, unless it's after a control. After a control, I could have a reorder buffer, and I could redirect everybody after that control thing to just read from the reorder buffer. And the reorder buffer read from the reservation station. Then I would only have to use the reorder buffer for things after a control. Then when it finishes, I could just launch the answer. Right? So I could make hybrid methods. Right? And that's, people do this, so what they do is they just look through and see, hey, how can I take care of them? Does it make sense? All right, so some strategies, right? Now we've talked about where they go and hopefully some of the implementation things, so you've got some ideas in your head. How do we actually chart where all these go? So let's say I had a piece of code. Let's even just take, let's imagine I had one back in here, so I don't have to write a new command. I'd like to be able to track this code and see, what does it look like? How can I actually find those answers that are going in? You know, from just a human standpoint, how do I record them? Well, just, even just on a board, how can I take a look at a code and write out where the problems are? Because there's a couple reasons we want to find problems. Right? Actually, several reasons. Imagine a problem gets discovered on your running machine. You know, and somebody says, this code sequence fails. You've got to be able to figure out, why does this code sequence fail? What most people do is they just start twiddling things until they get the right answer. But that just means you got the right answer. It doesn't mean it calculated it in the correct way. Any other thing could be even more wrong. You could have introduced more errors and not fixed anything. And you just luckily stumbled upon the correct answer. There's no guarantees that type of random flip until I get the answer I wanted for one thing. You know, that's crazy, right? So I might be trying to fix something and discover a problem. I could be trying to develop test cases to check a new machine that's out. How do I validate them? So I'm going to want to generate something that's going to have the errors and ensure that it'll have the type of errors I want to check. So I know that I get some good problematic test sequences. I could be thinking up a new problem and I want to see, will this problem work before I even try to start developing it to see if there's a chance where it goes on. So I need to, as a human, before I can build a machine or before I can fix a machine, I've got to understand a problem that it runs on, because we run off problems. We figure out a problem and then we can figure out how to solve it. If you don't have a problem and where it fails, right, you have no idea what you're doing. So you have no way to go forward. So when we're talking about how do we break this down, we want to get a way that we can visualize what's going on inside the programs so that we can generate a sequence to work on. So what we're going to do is draw this as a graph. So we're going to want to turn your code into a graph. And if I can look at a graph, right, where every node is an instruction, and then I can draw lines between the nodes to talk about the dependencies. I can change the style of print on the lines to tell you what type of dependence it is. So now you'll take a look at a graph, and if you ended up seeing a graph that looked like this, right? Can you tell me anything about that graph?
Seemed good to go.
Two things independent?
So what can I do with them?
That's parallel.
You could run them completely parallel. You don't know what those things are. But you could just look at that picture and immediately tell me that that's parallelizable. Right? So the advantage that the graph gives is I remove all the obstruction, because we look at this and we see moles and we see all kinds of other stuff that's going on. I've got a lot of things that are delaying me down in my head. Okay? I don't want to deal with that. I just want to get to what's the idea behind it. I can put costs on the nodes to let you know how long that thing takes. Right? So for some particular sequence coming in, I can say, hey look, here's the start of my sequence. I got data coming in from here. Boom, here we go. Here's the end of this little subroutine. Right? And you can see where they go. And I could ask you, hey, when is my answer good? Well, if I had in the thing here, this one takes 1 cycle, this takes 1 cycle, this takes 1, this takes 1, this takes 4, this takes 1. And I asked you, how long till the thing finishes? 6. Right? If that's the best you can do on each one in the sequence dependence, there we go, there's your answer. Right? Now, I could look at this and say, hey, maybe there was another sequence over here too. Let's say in addition to this, I had another thing that just went in. How long till it finishes?
6.
What if I only had 2 threads that I could run? How long would it take to finish? 6. Why?
It's still the biggest one.
Because for 2, I could run for the first 3, I could run this one on one thread. I could run that for the next 2. Well, on the second one, I'm running this. These 2 finish in 5. That one finishes in 6. I still finish in 6. How about now?
6.
I can still do it in 6. So I can do this forever, right?
No.
No. Now you're 7.
No, I'm 7. Right? Because I've got them into little parallel blocks. I can go 3, 4, 5, 6 on one pipeline, 6 on the other, but you're still stuck 1 on 1. What type of hazard is that?
Structural.
Structural. You give me an extra pipeline, that problem goes down. Right? You give me 3, I can go back down to what? 6. So now you gotta ask, is adding a 50% more hardware, is that worth a speed up of 1/7? Because it would have finished in 7, I can save 1, right?
Depends on the situation.
What's it worth, right? You gotta tell me that, all we can do is look at it and we can say this is the trade-off, we can quantify the trade-off. Somebody has to make a decision whether that's worthwhile. Right? But we want to get to the point where we can look at and start generating solutions, and then at this point I can fit in what instructions will do this. Right? That's where we want to get to. Does it make sense? Okay. So let's consider on this one. Right? What does this one look like? If I make each one of these things become some value, and I'm going to take my nodes, I'm going to split them in half. On the top one, I'm going to put a little identifier, which is kind of the command name. You could also write the load word command, whatever lets you know what it is. Right? Sometimes people write inside, sometimes people write above the node, whatever makes you happy. Right? And then for this one, I'm going to put an approximate cost on this one. So I'm going to say on average, maybe it's 4 cycles to finish. So you've got an idea of the weight that it's at. All right? Now, my second command, I've got the multiply. Does it rely on anything before it?
Not that we know of. Well, R1, yeah, okay, yeah.
Okay? So I look at this, and I just compare these with what's in here. The only thing in common is here, and that connection is a read after a write.
Yeah.
So this is a true dependence. That's going to be our nice little forward errors. Right? So this one is my multiply, and multiply is also expensive. I'm going to call it 8. How about 3?
Not depending, but you solve
So if the weight.
So what I have is I have the right after right. So it's really kind of an independent instruction. It's an add, so it's really fast. But there's this kind of name problem going on between them. So I'm going to do a dash line with no arrow. The no arrow tells you that there's no flow between these two. The dash just tells you there's a connected problem. Now, if I had a write after a read, there would be a flow order I didn't want. So an arrow would make sense. So a dash line with an arrow, you know it's a war. All right? So that's my convention. There is no universal convention I've seen on these things. You kind of got to pick up what somebody does. But I think it's a good idea to make sure when you do them, make your convention at least make sense so somebody can easily pick up what's going on. Does code have structural hazards?
Nice and short.
Seems like a lot of.
No. That's a problem with the hardware. You will never see it in the algorithm. So there's no sense trying to encode something that doesn't exist.